Unit 1, Lesson 6 is on trigonometric limits, and getting the results here is relatively straightforward. We're doing these trigonometric limits, I guess number 1 because you should know them, but number 2 so we can do calculus involving sine, cosine, tangent, things like that. Word of warning, we're also going for kind of accuracy of notation, taking care of every line, details, things like that. So your objective by the end of this, there are kind of 2 key trigonometric limits you need to memorize. Like a lot of other things, we just want to have them memorized, and in here I will show you where they come from. The other thing is we're going to follow the rules of trigonometry and algebra when rearranging. That's really going to be the main focus, kind of setting you up for success this year in looking at the details, not just looking at the result, but making sure what you're doing is mathematically accurate. Maybe that's the best way to say it. And as a reminder, your work is your answer. The thing at the end is just a conclusion. If the thing at the end is correct, but your work is magic or you haven't shown what you're doing, you haven't done a good job. You know, once we get past addition, subtraction, multiplication, division, you know, arithmetic-y sort of stuff in elementary school, math is that logical thought process. And so your job is in your work to kind of explain what you're thinking. So I guess we just kind of have to write more. So it is a huge error because there's a visual trick you can use to get the correct result. But the correct result does not mean you are correct. If you're like the students in my class, you'll see a trick and you will do not math. You will do things that aren't allowed by the rules of algebra, trigonometry, or whatever, using magic to move things around instead of doing actual algebra. Don't do that. Okay, so important limit number 1. If you're in my class, we did this as a warm-up. We graphed this. We did a numeric limit. So let's look at that. You know, when you do the limit as x approaches 0 of sine of x over x, the first thing you should think is, well, what would happen if I substitute in 0? And the answer is, well, sine of 0 is 0 over 0. Which is not no solution, is not undefined, is not anything like that. Because when we substitute, we're actually just pretending to do a limit. Because, well, it says the limit as x approaches 0, which means we're substituting in numbers closer and closer and closer to 0, not 0 itself. That substitution only works when we're doing continuity. So here's a graph from Desmos, and hopefully you would agree that as we look at this graph, choosing inputs closer and closer to 0 from the left and right, the graph of sine of x over x, well, the y values are definitely getting closer and closer to something. Now, I suppose another word of warning, whether it's Desmos or your graphing calculator, they're just graphing some points and connecting the dots in between. They're not magic. And so you kind of have to know, even though it's not written there, this graph has a removable discontinuity, a hole, a missing point, however you want to say that, at x equals 0. Anyways, so if we substitute in inputs a little bit less than 0, so here we're doing the limit as x approaches 0 from the left, we get 0.998, 0.99998, 0.99. It really appears that these y values are approaching 1 as x approaches 0 from the left. If we put in 0.1, 0.01, 0.001, notice we actually get the exact same y values for negative 0.1 and positive 0.1, negative 0.01 and positive 0.01. And that's because sine of x over x is an even function. Anyways, so point being, the limit as x approaches 0 of sine of x over x is 1. And so I suppose that's important limit number 1. You have to memorize that this is 1. Now, we'll get to it in a second, but a lot of people memorize this incorrectly, that sine of x over x is equal to 1. No, it's not. In fact, if you look at this graph, well, I only have part of it. In at least the part I've shown, and farther out, the peaks and troughs get closer and closer to the x-axis. They're shorter. Anyways, this graph actually never has a y value of 1. When we say the limit as x approaches 0 of sine of x over x is 1, what we're saying is as the x's get closer to 1, closer to 0 for both sides, the y values get closer to 1, even if they don't exactly get to 1. In this case, they don't. So what do you suppose the limit as x approaches 0 of x over sine x is? Well, there's a little bit of logic here, and we can handle this. If the limit as x approaches 0 of sine of x over x is equal to 1, what that means is the relative sizes of sine of x and x near 0 are about the same. Which means if we flip-flop numerator and denominator, sine of x and x near 0 still have about the same size. And you can see, as x approaches 0, it does indeed look like the limit as x approaches 0 of x over sine x does approach 1, which it does. Okay, important limit number 2. So the limit as x approaches 0, dark red, I like dark red better, of 1 minus cosine x over x. Well, what happens when we substitute? We should always be checking. So 1 minus cosine of 0 over 0. Cosine of 0 is 1. So we get another 0 over 0 indeterminate form, which again is not undefined, is not no solution, is not any of those, because all that means is 1 minus cosine x over x is not continuous at 0. Maybe we can figure this out by actually doing a limit. So looking at the graph, it definitely appears that this limit exists, and in fact is going to be equal to 0. So let's confirm that numerically. When we use negative 1/10, we get negative 0.0499. When we use negative 100, 1 minus cosine x over x is negative 0.00499. When we use negative 1,000th, 1 minus cosine x over x is negative 0.000499999. And we can tell, okay, those y values definitely look like they're approaching 0. That confirms the graph. And you can see when we use 1/10th, 1/10th, 100th, 1,000th, the limit as x approaches 0 from the left and the right of 1 minus cosine x over x, those are both going to 0. This limit is indeed equal to 0. So can you figure out, maybe we'll rewrite what we had, if the limit as x approaches 0 of 1 minus cosine x over x is equal to 0, what that means is, well, let's go back for a second. We went through the idea through substitution that we got 0 over 0. And I guess the question is, which one's shrinking faster, the numerator or denominator? Because notice, in all 6 of these cases and any other input, neither the numerator or denominator is actually 0. But they're both getting smaller and smaller and smaller. And because the outputs are getting closer and closer to 0, the numerator is shrinking faster than the denominator. So if we flip-flop, instead of 1 minus cosine x in the numerator, cosine x minus 1, we should get 0 as well. And we do, or another way to say that is cosine of x minus 1 over x is the negative version of 1 minus cosine x over x. And so, of course, well, that doesn't really affect the fact that at or near 0, the y values approach 0. Okay, here we go. So that was not very long ago. Do you know these limits from memory? The limit as x approaches 0 of sine x over x is 1, and the limit as x approaches 0 of 1 minus cosine x over x is 0. Now don't forget, we're actually, we should probably check first that we get an indeterminate form. Sine of 0 over 0 is 0 over 0. Okay, we can't do that by substitution. Likewise over here, 1 minus 1 over 0, that's 0 over 0. 1 minus cosine x over x. The limit does not, we can't do that through simple substitution using continuity. Okay, so let's try doing a few examples. The limit as x approaches pi halves of sine of x over x. What do we get? And the answer is not 1. The answer is, well, sine of x over x is continuous at pi halves. We always want to check by substituting. And when we substitute in pi halves, sine of pi halves is 1. So we don't need to use this rule because we don't have a weird indeterminate form 0 over 0. A lot of people will write 1, and I think I said that earlier, because people memorize incorrectly. Sine of x over x is equal to 1. No, it's not. Sine of x over x, right, that was a graph that looked like this. Sine of x over x approaches 0. But, you know, way over here at pi halves, yeah, we definitely don't get 0. We get 2 over pi. Let's try that again. What about the limit as x approaches pi of 1 minus cosine x over x? Hopefully after that last example, you're not thinking 0. We're thinking, well, gosh, let's substitute in pi. And cosine of pi is -1. So 1 minus -1 is 2, still over pi. Again, we don't need these trigonometric limits if we don't need the memorized ones if we can do these through simple substitution with continuity. Are we going to have to do some hard work here? No, again, is sine of x over x continuous at pi? It sure is. So we're just going to substitute in pi. Sine of pi is 0, divided by pi is 0. Now you're getting it? I used to teach this the other way. I just do our new rules. But people used to screw it up. So I like to start off with when you don't use this, because that's by far the more common case. Okay, so here we go. Limit as x approaches 0 of sine of x over x. Is sine of x over x continuous at 0? No. And if we did substitute, we would get 0 over 0. Oh, right. This is that memorized one. We just get 1. And it's assumed if you write 1, you're doing it correctly, you understand, you've memorized, you don't really need any work. Now the other thing is, I write this as the limit as x approaches 0 of sine of x over x is 1. And I don't know if you want to call it substitution, or eventually it'll make sense when we do the chain rule or something like that. But it's actually the limit as x approaches 0 of sine of stuff over stuff is equal to 1, and those things can match. As in, it doesn't have to be just x. Let's show you. So you might see it this way. Limit as x approaches 0 of sine of a function over that same function. We use u to denote a function. That's going to be equal to 1. So let me show you what I mean. So the limit as x approaches 0 of sine of 2x over x. Well, if we substitute, we get sine of 0, which is 0, over 0, which is 0, in determinate form. Now, this is not equal to 1. We want the limit as x approaches 0 of sine of stuff over stuff, and then we'll know that's 1. So we need to think, well, man, can I, you know, you kind of have two choices. Either put a 2 in the denominator or get rid of the 2 in the numerator. And this is the use algebra, use trigonometry, not magic sort of thing I was referring to earlier. And so the easier way is to get a 2 down here because the 2x in the numerator is locked up inside of the sign. But of course we can't just write a 2. Notice there are no equal signs. So really we kind of divided by 2. So instead of that, what we do is multiply and divide by 2. Because essentially what we've done here is multiplied by 2 over 2. When you multiply by 1, obviously we don't get a change in value. We just get a change in structure here. And so now notice we have this form. The limit as x approaches 0 of sine of 2x over 2x, or sine of stuff over the same stuff. That's going to be equal to 1, but that 2 comes down. So we just get 2. Now, don't go based on faith. You should always check all of these rules. I mean, somebody made them up, and they're probably not lying to you, but your job is to understand things, not just to get the results. And so, on Desmos, I graph this, and you can, you know, I bet you can't click on this link, but I don't know, type it in, whatever. And you can see sine of 2x over x near 0 does indeed approach 2. If you want some numerical values, I substituted those in as well, or made Desmos do it, and those numerical values should also kind of confirm what's going on. All right, so how are we going to evaluate the limit as x approaches 0 of sine of 5x over 3x? Well, first thing, we need to substitute. And when we substitute, we get sine of 0, which is 0, over 0, which is 0. Now, I'm doing this in my head. If I get 0 over 0, though, I'm like, well, can I rearrange? No, sine and that algebraic 3x can't be rearranged. And so I guess what I'm thinking is, man, I'd really like to have a 5 where that 3 is. So what I'm going to do is move that 3 out of the way. Because, well, as long as it's not this variable x, we can pull any other multiplier out front. And so now I have space. I want to put a 5 right here. But of course, I can't just write a 5. The only thing I can multiply by without changing values is 1. So I'll multiply by 5 over 5. And now, well, the 5/3 comes down. And the limit as x approaches 0 of sine of stuff over the same stuff, sine of 5x over that same 5x, is 1. So we just get 5/3. Now over here on the right, this is the kind of magic I was talking about. And, you know, that 5/3 at the end matches the 5/3 here at the beginning. But if you say, oh, I'm allowed to pull this 5 out front, well, I suppose you're wrong. Now, that's a neat trick and all if you're doing multiple choice, but I really don't think you understand the rules of trigonometry, which means you're going to get a whole bunch of stuff wrong. And so you need to understand how to move things around. Let me say that another way. The math on the right is not correct. It's not math, it's magic. So if this is a quiz, if this is a test, if this is the AP test, from here to here, while numerically they're correct, you're not going to get credit because, well, it's clear you don't understand the rules of trigonometry. So weirdly, the 5/3 on the left is correct and the 5/3 on the right is wrong. Okay, what do we do here? The limit as x approaches pi of x over sine of 2x. Do you remember what happens when we flip-flop numerator and denominator? X over sine of 2x? And you might be thinking, well, still 1, but you'd be wrong. Because, well, that's the limit as x approaches pi, not the limit as x approaches 0. So what happens when we substitute? Well, we get pi divided by 0. Now, pi is a constant, 3.14159, whatever. But the numerator actually doesn't really get to pi because with a limit, we're substituting numbers near pi. And the denominator doesn't really get to 0. So what we're getting is like 3.14 divided by 0.1. 3.141 divided by 0.01, stuff like that. And what you can see is we're getting unbounded growth. And so whenever you get a constant over 0, that limit does not exist because, well, if you graph, you'd see it too. Unbounded growth, an infinite discontinuity, a vertical asymptote, something like that. So in this case, we substitute. We always want to check continuity. 0 over sine of 0. Oh, that's the one. So in this case, we need to get stuff over sine of stuff, and then that limit will be 1. So can we change the numerator x, or do we change the denominator sine of 2x? And the answer is we need a 2 in the numerator. We can't touch the 2x down here. And we can't just multiply by 2. We have to multiply by 2 over 2, a version of 1. Bring down the 1/2, and that limit of, as x approaches 0 of 2x over sine of 2x is 1. Ooh. I always seem to run out of time. The limit as x approaches 0 of sine of 5x over sine of 2x. This one seems difficult. And I suppose it is, but there's a little trick here. When you substitute, we definitely get 0 over 0. So We can't combine the two signs. They have different arguments, so they don't divide to be 1 or something like that. So what we need to do is give ourselves some room. So I'm going to write the sine of 5x over, well, nothing for a moment. I'm going to put something there in a minute. And the sine of 2x under nothing. And then I think, well, what do I want? I'd really like to have a 5 underneath the sine of 5x. So I'll do kind of what we did before and put a 5 underneath the sine of 5x and a 5 in the numerator out front, because that other one's just going to be in the way. I suppose you could have put it here at the end, 5 over. I just like to have it out front. Anyways, what do we want above? Well, wait, no, we want a sine of 5x over 5x. So where do I put the other x? And the answer is not out front. We can't put an x out here. You can't bring out anything involving, well, x, because we're doing the limit as x approaches 0. But remember, I do want an x over here. Eventually, I'm going to want 2x over sine of 2x. So I'll put that x up here. And then all I need to do is get a pair of 2's. And then that works out. So bring down the 5 halves. Limit as x approaches 0 of sine of 5x over 5x is 1. 2x over sine of 2x goes to 1 as x goes to 0, right? Because we're doing the limit of both of these. If you want to, you could even write, limit here or something like that. All right, I hope that helps.